In this video, we are going to focus on organic chemistry, structure and properties of alkanes. We're going to see how to describe and generalize the structure of alkanes and cycloalkanes. We're going to look at IUPAC rules for nomenclature, then compare the physical properties of alkane molecule. We're going to construct structural and conformational isomers and compare the relative energy and stabilities, predict the outcome of combustion and halogenation reactions of alkanes, and identify geometric isomers in cycloalkanes. So let's begin. Classification of hydrocarbons. The study of organic compounds begin with alkanes because alkane structures form the hydrocarbon backbone of most organic compounds. Hydrocarbons are molecules that are made up of hydrogen and carbon only. A hydrocarbon with no double bond or triple bond are said to be saturated because it has maximum number of bonded hydrogen. We classify hydrocarbons according to their bonding as shown in the figure. Alkanes have only single bonds. A hydrocarbon with a carbon-carbon double bond, such as ethylene, is an alkene. If a hydrocarbon has a carbon-carbon triple bond, like acetylene, it is an alkyne. Hydrocarbon with aromatic rings resembling benzene are called aromatic hydrocarbons. A hydrocarbon with no double or triple bond is said to be saturated because it has the maximum number of bonded hydrogen. Another way to describe alkane then is a class of saturated hydrocarbon. Molecular formula for alkane. The general formula of alkane is CnH2n plus 2. Alkanes are found in everything from natural gas to petroleum. The smaller alkanes have very low boiling point, therefore they are gases. Alkanes differ only with number of methylene group in a chain. Homologous series is a series of compound whose members differ by a repeating unit. For example, alkane. Alkane differ by a methylene group. Alkanes are usually sp3 hybridized and bonds are sigma bonds. Some examples of alkanes include methane, ethane, propane, butane, and isobutane. Notice that all atoms in alkanes are sp3 hybridized and the bonds are sigma bonds. Although we have derived the CnH2n plus 2 formula using unbranched N-alkanes, it applies to branched alkanes as well. Any isomer of one of these N-alkanes has the same molecular formula. Just as butane and pentane follows the CnH2n plus 2 rule, their branch isomers like isobutane, isopentane, and neopentane also follows the same rule. Nomenclature of alkanes. The name of all alkanes end with "ane", and a Greek word is used for the number of carbon atoms. For example, C4H10. There are two isomers for formula C4H10. The unbranched isomer is simply called butane or N-butane, meaning normal butane, and the branched isomer is called isobutane, meaning isomer of butane. Constitutional isomers are compounds with the same molecular formula, but the carbons are connected differently. IUPAC stands for International Union of Pure and Applied Chemistry. Common names kept are methane, ethane, propane, and butane. Meth, eth, prop, and but in these names are the root names. Alkane, for example, suffix "ane" will be used after the number of carbons. For example, an alkane with 5 carbon is penta for 5 and suffix "ane" will be used, so the compound will be called pentane. Four rules govern this process: main chain, numbering the main chain, naming alkyl group, and organizing multiple groups. Let's look at one by one. Rule number 1. Find the longest continuous chain of the carbon atom and use the name of this chain as the base name of the compound. So the first rule of nomenclature gives the base name of the compound. The group attached to the main chain are called substituents because they are substituted in place of hydrogen atom on the main chain. When there are two longest chain of equal length, use the chain with greater number of substituents as the main chain. Following compounds contain two different 7 carbon chain and is named as heptane. We choose the chain on the right as the main chain because it has more substituent in red to the chain. To give the location of substituent, assign a number to each carbon atom on the main chain. Rule number 2 is number the longest chain beginning with end of the chain nearest a substituent. We start numbering from the end nearest a branch so that the number of substituent carbon will be as low as possible. In the preceding heptane structure on the right, numbering from top to bottom gives the first branch at C3, carbon atom 3, but numbering from bottom to top gives the first branch at C2 or carbon 2. Numbering from bottom to top is correct. If each end had a substituent the same distance in, we would start at the end nearer the second branch. Name the substituent group. Rule number 3 is name the substituent groups attached to the longest chain as alkyl group. Give the location of each alkyl group by the number of main chain carbon atoms to which it is attached. Alkyl groups are named by replacing the "ane" suffix of the alkane name with the "yl". Methane becomes methyl, ethane becomes ethyl, and so on. You may encounter the word amyl, which is an archaic term for a pentyl 5 carbon group. The figure on the right gives the name of most common alkyl groups, those having up to 4 carbon atoms. The propyl and butyl group are simply unbranched 3 and 4 carbon alkyl group. These groups are sometimes named N-propyl and N-butyl to distinguish them from any other kind of branched propyl and butyl groups. The names of secondary butyl and tertiary butyl or groups are based on the degree of alkyl substitution of carbon atom attached to the main chain. In the secondary butyl group, the carbon atom bonded to the main chain is secondary or bonded to two other carbon atoms. In tertiary butyl group, it is tertiary or bonded to three carbon atoms. In both the N-butyl group and isobutyl group, the carbon atoms bonded to the main chain are primary, bonded to only one other carbon atom. So primary carbon, first degree carbon atom bond to only one carbon, second degree carbon atom bond to two carbons, and third degree carbon they bond to three carbons. The final rule deals with naming compounds with more than one substituent. When two or more substituents are present, list them in alphabetical order. When two or more of the same alkyl substituent are present, use prefixes like di, tri, tetra, etc. to avoid having to name the alkyl group twice. Include a position number for each substituent even if it means repeating a number more than once. Di means 2, tri means 3, tetra means 4, and so on. Using this rule, we can construct name for some complicated structure. Let's finish the name of the heptane shown again here in the corner. This compound has an ethyl group on C3 and 3 methyl group on C2, C4 and C5. List the ethyl groups alphabetically before the methyl group and give each of the 4 substituent a location number. So the compound name will be 3-ethyl 2,4,5 trimethyl heptane. Heptane means the compound have 7 carbon main chain, trimethyl 2,4,5. On second carbon, fourth carbon and fifth carbon there is a methyl group present. and on the third carbon ethyl group is present. Physical properties of alkanes. Alkanes are used primarily as fuels, solvent and lubricant. Natural gas, gasoline, kerosene, heating oil, lubricating oil and paraffin waxes are all composed of primarily of alkanes with different physical properties resulting from different range of molecular weights. So let's look at first property, solubilities and densities of alkanes. Alkanes are non-polar, so they dissolve in non-polar or weakly polar organic solvent. Alkanes are said to be hydrophobic, water-hating, because they do not dissolve in water. Alkanes are good lubricants and preservative for metals because they keep water from reaching the metal surface and causing corrosion. Alkanes have densities around 0.7 grams per milliliter, compared with a density of 1.0 gram per ml for water. Because alkanes are less dense than water and insoluble in water, a mixture of an alkane such as gasoline or oil and water quickly separates into two phases, with alkanes on the top. Figure on the left shows oil floats on water. Note how oil from the 2010 blowout of Macondo well in the Gulf of Mexico floats on top of water where it can be burnt off. Oil recovery booms containing non-polar fibers are used to soak up and contain the floating oil. Note how most of the burning oil ends at the oil recovery boom. Boiling points of alkanes. The boiling point increases smoothly with increasing number of carbon atoms and increasing molecular weight. Larger molecules have larger surface area resulting in increased intermolecular van der Waals attraction. These increased attraction must be overcome by vaporization and boiling to occur. Thus, a larger molecule with greater surface area and greater van der Waals attraction boils at a high temperature. A graph of n alkane boiling points versus the number of carbon atom, the blue line in figure shows that boiling point increases with increasing molecular weight. Each additional CH2 group increases the boiling point by about 30 degrees Celsius up to about 10 carbons and by 20 degrees Celsius in higher alkane. The green line in figure represents the boiling point of some branched alkanes. In general, a branched alkane boils at a lower temperature than the N-alkane with same number of carbon atom. This differences in boiling point arises because branched alkanes are more compact with less surface area for London force interactions. Next we have melting point of alkanes. The blue line in figure is a graph of melting point of N-alkanes. Like their boiling points, the melting point increases with increasing molecular weight. The melting point graph is not smooth, however, alkanes with even number of carbon atoms pack better in a solid structure, so higher temperatures are needed to melt them. Alkanes with odd number of carbon atoms do not pack well and they melt at lower temperature. The sawtooth shaped graph of melting point is smoothed by drawing separate lines, green and red, for alkanes with even and odd number of carbon atoms. Reaction of alkanes. Alkanes are the least reactive class of organic compounds. Their low reactivity is reflected in another term of alkane, paraffins. The paraffin comes from two Latin terms, param meaning too little and affins mean affinity. Reaction of alkanes include combustion, cracking, hydrocracking, and halogenation. Combustion is a rapid oxidation that takes place at higher temperature, converting alkanes to carbon dioxide and water. Little control over the reaction is possible except for moderating the temperature and controlling the fuel or air ratio to achieve efficient burning. Cracking. Cracking of large hydrocarbons at high temperature produces smaller hydrocarbons. The cracking process usually operates under conditions that give the maximum yield of gasoline. In hydrocracking, hydrogen is added to give saturated hydrocarbons. Cracking without hydrogen gives mixtures of alkanes and alkanes. Halogenation. Alkanes can react with halogens, for example fluorine, chlorine, bromine, and iodine, to form alkyl halide. For example, methane reacts with chlorine to form chloromethane, dichloromethane, trichloromethane, and tetrachloromethane. Heat or light is usually needed to initiate this halogen process. Reaction of alkanes with chlorine and bromine proceeds at moderate rate and are easily controlled. Reaction with fluorines are often too fast to control. However, iodine reacts very slowly or not at all. Structure of methane. The simplest alkane is methane, CH4. Methane is perfectly tetrahedral with the 109.5 degrees bond angles predicted for an sp3 hybridized carbon. Four hydrogen atoms are covalently bonded to the central carbon atom with bond length of 1.09 angstrom units. Conformation of ethane. Ethane, the two-carbon alkane, is composed of two methyl groups with overlapping sp3 hybrid orbitals, forming a sigma bond between them. The two methyl groups are not fixed in single position but are relatively free to rotate about the sigma bond connecting the two carbon atoms. The bond maintains its linear bonding overlap as the carbon or atoms turn. The different arrangements formed by rotation about a single bond are called conformations, and a specific conformation is called a conformer or conformational isomers. Pure conformers cannot be isolated in most cases because the molecules are constantly rotating through all possible conformations. In drawing conformations, we often use Newman projections, a way of drawing a molecules looking straight down the bond connecting two carbon atoms. The front carbon atom is represented by three lines or three bonds coming together in a Y shape. The back carbon is represented by a circle with three bonds pointing out from it. The conformation with dihedral angle equals 0 degrees is called the eclipsed conformation because the Newman projection shows the hydrogen atom on the back carbon to be hidden by those on the front carbon. The staggered conformation with dihedral angle equals 60 degrees has the hydrogen atom on the back carbon staggered halfway between the hydrogen atom on the front carbon. Any other intermediate conformation is called a skew conformation. Conformation of ethane. An infinite number of conformations are possible for ethane because the angle between hydrogen atoms on the front and back carbon can take an infinite numbers of values. The figure shows how the potential energy of ethane changes as the carbon-carbon bond rotates. The y-axis shows the potential energy relative to the most stable staggered conformation. The x-axis shows the dihedral angle as it increases from 0 degrees eclipsed through 60 degrees staggered, and on through additional eclipsed and staggered conformation as dihedral angle continues to increase. As ethane rotates toward an eclipsed conformation, its potential energy increases and there is a resistance to rotation. This resistance to torsion is called torsional strain, and the 12.6 kilojoules per mole of energy required is called torsional energy. Conformation of propane. Propane is a 3-carbon alkane with formula C3H8. The figure at the bottom represents a Newman projection looking down one of the carbon-carbon bonds. The graph shows the torsional energy of propane as one of the carbon-carbon bonds rotate. The torsional energy of the eclipsed conformation is about 13.8 kilojoules per mole, only 1.2 kilojoules more than that required for ethane. Apparently, the torsional strain resulting from eclipsing a carbon-hydrogen bond with a carbon-methyl bond is only 1.2 kilojoules, more than the strain of eclipsing two carbon-hydrogen bonds. The staggered conformation of propane is lower in energy than the eclipsed conformation. Since the methyl group occupies more space than a hydrogen, the torsional strain will be 0.3 kilocalories per mole higher for propane than for ethane. Conformations of butane. Butane is the 4-carbon alkane with molecular formula C4H10. We refer to N-butane as straight chain alkane, but the chain of carbon atom is not really straight. The angles between carbon atoms are close to tetrahedral angle about 109.5 degrees. Rotation about any of the carbon-carbon bonds are possible. Rotation about either of the end bonds just rotate a methyl group like they do in ethane and propane. Rotations about the central C2 or C3 bonds are more interesting. The figure shows the Newman projections looking along the central C2-C3 bonds for 4 conformation of butane. From the 4 conformations, 3 of them are given a special name. When the methyl groups are pointed in the same direction, dihedral angles equal 0 degrees, they eclipse each other. This conformation is called totally eclipsed. To distinguish it from the other eclipsed conformations such as the one at dihedral angle of 120 degrees. At the dihedral angle of 60 degrees, the butane molecule is staggered and the methyl groups are towards the left and right of each other. This 60-degree conformation is called gauche, a French word meaning left or awkward. Another staggered conformation occurs at the dihedral angle of 180 degree. With methyl groups pointing in opposite direction, this conformation is called anti because the methyl groups are opposed. Torsional energy of butane. A graph of relative torsional energy of butane conformation is shown. All the staggered conformation, anti and gauche, are lower in energy than any of the eclipsed conformation. The anti-conformation is lowest in energy because it places the bulky methyl group as far apart as possible. The gauche conformation with the methyl group separate by just 60 degrees are 3.8 kilojoules higher in energy than the anti-conformation because the methyl groups are close enough that their electron clouds begin to repel each other. Steric strain. The totally eclipsed conformation is about 6 kilojoules higher in energy than other eclipsed conformations because it forces the two end methyl groups so close together that their electron cloud experience a strong repulsion. This kind of interference between two bulky groups is called steric strain. The following structure shows the interference between the methyl group in totally eclipsed conformations. Rotating the eclipsed conformation 60 degrees to a gauche conformation releases most but not all of this steric strain. The gauche conformation is still 3.8 kilojoules higher in energy than most stable anti-conformations. Cycloalkanes are alkanes that contain rings of carbon atoms. Simple cycloalkanes are named like acyclic, non-acyclic alkanes with the prefix cyclo indicating the presence of ring. For example, the cycloalkane with 3 carbon atoms in a ring is called cyclopropane. Line angle formulas are often used for drawing the rings of cycloalkanes. Simple cycloalkanes are ring of CH2 groups or methylene groups. Each one has exactly twice as many hydrogen atoms as carbon atoms, giving the general formula of CnH2n. This general formula has two fewer hydrogen atoms than the formula of an acyclic alkane because the ring has no end and no hydrogen are needed to cap off the ends of a chain. Most cycloalkanes resemble the acyclic open-chain alkanes in their physical properties and in their chemistry. They are nonpolar, relatively inert, and the boiling point and melting point of them are depend on molecular weight. The cycloalkanes are held in more compact cyclic shape, so their physical properties are similar to those of a compact branched alkanes. Nomenclature of cycloalkane. When naming cycloalkanes, the IUPAC nomenclature rules can be applied with following adaptations. Use cycloalkane as the parent name for substituted cycloalkanes and name the alkyl group as substituents. There is no need to number the substituent if there is only one substituent. If there is more than one substituent on the ring, the carbon in the rings are numbered to give the substituent the lowest possible number. If there are two substituents and the numbering could start at any of the two substituents, then numbering should start at the alkyl group, that is, first alphabetically. If straight chain portion has more carbon atoms than the ring, then cyclic part is substituent, which is named as a cycloalkyl group. The parent name is determined by the length of the straight chain. According to the IUPAC convention, if the longest continuous carbon chain is a ring, the prefix cyclo must be used. The chain contains 5 carbon atoms and thus the parent name is pentane. Begin numbering at a branch to give substituent the lowest possible number. For instance, at the carbon with 2 substituents, thus on the C1 is an ethyl group indicated as 1-ethyl. There is methyl on C1 shown as 1-methyl, and there is also a methyl group on C3 which is indicated as 3-methyl. The two methyl groups are written as 1,3 dimethyl. List the substituents in the alphabetical order. So the IUPAC name for the following compound will be 1-ethyl 1,3-dimethyl cyclopentane. Cis and trans isomerism in cycloalkanes. Open chain or acyclic alkanes undergo rotation about their carbon-carbon single bonds, so they are free to assume any of an infinite number of conformations. Alkenes have a rigid double bond that prevents rotation, giving rise to cis and trans isomers with different orientation of the group on the double bonds. Cycloalkanes are similar to alkenes in this respect. A cycloalkane has two distinct faces. If two substituents point towards the same face, they are cis. If they are pointing towards the opposite faces, they are trans. These geometric isomers cannot interconvert without breaking and reforming bonds. This brings us to the end of structure and stereochemistry of alkanes. Thank you for watching. If you like my video, don't forget to subscribe for more.